Well, hello, everybody. Welcome back to DeepRob for discussion 4. So today's discussion, the goal is for it to be kind of a collaborative, so you can start to form groups or start to kind of coalesce around some shared interests. And really what we're going to do today is go over kind of at a broad view some of the core kind of topic areas that we've kind of identified for the final projects that you'll be working on in the second half of the semester. So at last lecture on Thursday, we introduced kind of more officially during the lecture time what to expect for the final project coming up. And so today's discussion will give an overview of the topics and some of the papers, although we won't probably have time to kind of go through all of the papers at a little bit more detail, so you can start to understand what types of projects are available and hopefully find some of them that are interesting. The other thing I will mention is that if you open Gradescope, what you should see now is there's like a week-long quiz. So I'll make an email announcement about this after discussion so that everybody's aware of it. But so this quiz will be one of the 16. So, and you have a week to take it. And what it is not a quiz. It's just a survey of what topics from our selected areas you find the most interesting. So there should be no time limit on it. You should have the full week until next Friday at midnight. And the goal is you can identify like your top 3 areas, and then we'll do our best to match you with your areas of like highest interest. So if you have issues with the quiz or there's a time limit or anything like that, let me know, because it's hard on my end of Gradescope to sometimes see what the students see. Okay, but with that, let's get right into it. So what I've done in kind of the slide decks here is kind of collect the core papers that we've identified for some of the topic areas. And what I want to kind of do during this discussion is walk through at a high level kind of what the maybe motivating themes within these areas that I've selected are, and then talk a little bit about some of the papers that are highlighted. And so these will be papers that you'll ultimately be presenting for the final project. And the thing then that I want to kind of maybe talk over, so I didn't go into this too much in detail at Thursday's lecture, but I'll try to do it more in detail on next week's lectures. So the way that the paper presentation and the paper review portion of the final project is going to work is we've selected a set of these topic areas under the paper page of our website, and each of these topic areas they represent broadly some of the ways that you can apply deep learning to robot perception. So for example, like RGBD architectures would be the set of methods that try to take color and depth images together as input and process them for some downstream robotic task, maybe like manipulating objects in the scene. In contrast then, maybe a topic like, let's say, sorry for me to see, like, dense object descriptors and category level representations. So that's kind of a more niche area of work that tries to say, okay, we have neural network representations for rigid body objects, but maybe they're kind of overly tuned to just a set of known kind of like instance level objects. But what if we wanted to represent an entire category? So instead of having one neural network model that could identify this specific type of chair, and then having a different neural network model that could identify this, still a chair, but a different set of chair, maybe I just want one neural network that could identify the entire category of chairs, like altogether. So that's what that class of work looks at. And so within these areas, each area then maps to a week, one of the weeks within our, or maybe actually half a week, because we have 2 areas per week in our schedule. But within these areas, what we've done is we've identified a core list and then an extended list of relevant papers. So this is not a complete list of all the papers and all the work that's been done in these areas. Hopefully that's apparent. But what we tried to do in the core list is select a set of papers that gives broad coverage of the areas, generally focuses on very prominent works that tend to be highly cited, and really to give you a sense of what is the state of the art and to some extent what's been the kind of recent trends. So we tried to pick them so that they're not like all from 2022 ICRA, right? We're trying to give you some sense of what the trends are in the field, but still focusing on, for the core list, on sets of work that you'll see cited quite frequently. In the extended list, then, we have additional papers that if just you're interested in that area and you want to like really expand your knowledge even more, you can refer to that extended list for just additional references. But in terms of what you'll be presenting or reviewing, there'll always be papers from the core list. So generally, there's 4 to 5 papers per core list section. So before we start looking at some of these papers and talking a bit more about these areas, let me pause and see if I can answer administrative questions or just questions about the structure of what we've been talking about here with the papers and how it relates to the final project. We're trying to kind of give like a lot of leeway, like a lot of heads up ahead of the actual project starting, just so that no one's caught off guard. So the paper presentations will be within your group. So it'll be like if you want to work in a group, like up to 3 people will present a paper. And the way that we'll organize the groups is based on the survey. So you should answer the survey based on like your areas of interest. And then we're going to match groups based on people who have overlapping areas of interest. Yes, this group will also be for the final project. If you have issues or concerns, then you can come and contact the core staff if you feel you need to have a different group. Yeah. Mm-hmm.
In that case, groups are random.
Groups will be, well, they're random, conditioned on your areas of interest. Yeah. Sure. Yeah. Okay. All right. So let's start to kind of look at some of these areas. So the first topic area, which will start in week 8, is what we call these RGBD architectures. So like I was saying, so for a lot of robots, it's very, very inexpensive to put a camera on the robot. And in addition to that, there's a specialized type of camera that will not only collect color information in the RGB channels like we've been looking at, but also give you the depth of every single pixel within the image. So the way that works is if you imagine a ray extending from like the focal point of the camera out through one of the pixels and then into the world, the length of that ray, once it hits the closest object, would be the depth of that corresponding pixel. And so these RGBD networks can be very, very powerful for when you want to start working in 3D space. So maybe when you want your robot to start estimating the pose, like we were talking about in some of the past discussions, having that depth input in addition to the color input can make your accuracy for pose estimation go up. And so some of the core papers that we've identified here, so Pose CNN is one very, very famous paper where they apply deep learning-based pose estimation on an RGB image, and then they add depth as sort of a fine-tuning step to, kind of at the end or just outside of the actual network. Then there was an interesting work on this unified multi-class pose estimation, which actually suggested like combining both the RGB and the depth channels as both being input to the deep neural network for regressing the actual object pose. And then more recently, there's been some works that look at like how you could maybe use other representations of pose beyond just like rigid body 6 degree of freedom pose, but actually like trying to estimate pose based on key points on a specific object. So this PVN 3D paper, for example, and then even using RGBD to actually just extract information out of the images that you're collecting to embed the images in some learned feature space and using that for some downstream tasks. So the core idea with RGBD networks, though, is you're moving from just color space input to now color plus depth information as input. And so like I was saying, so for like 3D space, for trying to estimate things in the 3D world, that depth channel is very, very important. So following on from that, then the second topic of final projects is going to be the point cloud processing area. So this is kind of similar to the RGBD networks, where instead of trying to treat the input to our neural networks as just like images, instead what we might have are point clouds. So some depth cameras, for example, you could interpret their the depth for every pixel as actually being a point within 3D space. So if you know where the camera is within 3D space, you can imagine sort of rendering out those rays into 3D space, and then where those rays hit an object is a point. And so if you treat now your input data as this point cloud, then you could try and have some neural network that maybe tries to like classify what shape you're looking at based on the points in the input. And so PointNet, for example, applied that idea to semantic segmentation of point clouds, and then PointNet++ sort of looked at how you could extend PointNet for like these kind of point cloud classification problems. But they've been used additionally in other tasks. So for example, pose estimation. So dense fusion is one work that you'll see commonly cited within pose estimation. that uses point clouds. And in addition, point fusion is another interesting paper that looks at like 3D, like if you're trying to, for example, like in an autonomous car setting, if you're trying to detect like 3D bounding boxes around obstacles and you have point cloud data, you can do some interesting processing there. So those two areas, that RGBD networks and point cloud processing, so those will tie together for week 8. And building on top of that then, and we've still been talking mostly about either classification or segmentation in the case of PointNet, or pose estimation, which will be brought up in some past discussions. And so how it is you represent pose within deep learning is an interesting question. And so how you represent sort of the pose of an object, or just describe an object more generally. So some work that actually came out of Professor Jenkins' lab, so this sequential scene understanding paper, for example, is an interesting one where it tries to combine deep learning with some more traditional like particle filtering techniques to estimate pose. So it's like, how can we kind of combine sort of classical methods for pose estimation with deep learning based methods. But then on the topic of how it is you represent the geometry of an object or the actual shape of an object, there's a term called, or a kind of technique called sign distance function, where if you imagine some object, so maybe like this microphone that I'm holding, it has a surface, right? And so if you wanted to represent that geometry, that surface geometry in a computer, there's different ways you could do that. So from computer graphics, you could represent it as like a mesh model, right? Where you have a set of vertices and edges connecting those vertices to represent the surface. And that is one way that you can do it. So in those more classical pose estimation techniques, sometimes what you'll see is they'll use the mesh model and they'll sort of render the mesh model into an estimated pose and then see how well it aligns with an observation. But it turns out that actually neural networks can represent these geometries in kind of more, or I should say it like this. There are other representations of object geometry that neural networks can represent and might actually be better for these downstream tasks like pose estimation. So the sign distance function, what that tries to learn in a neural network is, instead of like a discrete just set of vertices, it tries to learn a function that would tell you for any 3D point in XYZ space, how kind of far away am I from the nearest point on the surface of some object? So you might learn a neural network that would represent this specific microphone as a sign distance function. And then what you could do is you could query that network, like tell me for this point where my finger is, how far away am I from the surface? And if you kind of imagine like you keep querying it, that network until you get closer, you could find then like a level set of, let's say, like scores from your output of your network, and that level set of points could then describe an object. So the reason why that's useful is like the neural networks turn out to be really, really good at learning these sign distance functions. And so you can use these like learned feature representations as components of some other downstream network. Like if you wanted to have a pose estimator network, you could maybe first learn like a sign distance function of an object and then incorporate that learned sign distance function into some downstream task. So the sign distance function would be one example of what you might call like an implicit surface. So what we mean by implicit, you'll see this term come up quite a bit in literature, is this idea that like there's a scene or there's an object geometry that exists in the physical world, and you're trying to encode all of the information about that geometry or about that scene into some like hidden implicit representation that is the neural network parameters. So no longer do you have like explicit vertices maybe in like an object, like an OBJ file for an object, but baked into that neural network that learned the sign distance function, it's like it still knows all of that information. It's implicit. All that information is implicit within that neural network. So in like the neural radiance field literature, that's also an implicit representation of some full scene. So yeah, so object pose, geometry, sign distance functions. Building on that then, the one kind of downside or one caveat with some of those works is that they tend to be sort of fine-tuned on sort of instances within a category of objects, right? So maybe you have to learn a sign distance function just for this microphone. And then like I was saying in the example of a chair, it's very inefficient to have to learn like a different network representation for all the possible objects that our robots might be perceiving or we might want to act on. So instead, there's a really interesting question that comes up, which is, let's say that I want to still maybe represent some object using a learned representation. How can I do that at the category level instead of the instance level? So how can I extend some of those ideas on like pose estimation or like representing objects implicitly, but not to just work on an instance of a single object, but to instead work on the entire class of objects that you might see. And so these works here are some that have been very, very successful within these categories of like category level representations, but also dense object descriptors. So like normalized object coordinate space, for example, will try to represent like all of these cameras in the same like normalized space, which can be very beneficial for training like a pose estimation task, because you could now train it to perform category level tasks where previously maybe they could only work on instance level tasks. So this relates to some extent, so like this normalized object coordinate space example relates also to what we left off at last lecture on that concept of batch normalization. So it's an interesting idea that how you transform your input data can have drastic consequences on the downstream performance of some of your applications. So it's an interesting thing to think about. Like if you have some new application, you might need to come up with an interesting normalization technique for your networks to perform well. Another really interesting one is, I mean, all of these are extremely interesting, but KPAM, for example, proposed representing for trying to estimate like the pose of an object and an entire category of objects. Don't try and estimate the origin as 6 degrees of freedom. So don't try and estimate like the XYZ and roll pitch yaw of the origin of this object. Instead, pick maybe like 3 key points on this category of objects. So in the case of a microphone, maybe you pick like the very top where the like actual audio is going into, and maybe like the very bottom. And you would just try and estimate the XYZ position of those 2 key points, and then from that use a classical approach to derive the 6 degrees of freedom representation of pose from those 2 key points. And found that it was extremely effective for robot manipulation tasks. So essentially, like the neural networks were very, very effective at learning how they could estimate the position of these key points on different object classes, even on unseen instances of the object. So maybe like what they did that was really interesting is like they could train their key point detector maybe on like this chair and let's say also like one of these chairs that you're sitting on, but then they could apply their method on an unseen chair, and it would still work for like to a very high degree, and even so effectively that robots could still manipulate like mugs and these types of like handheld objects effectively. So it'd be like you trained it on these two chairs to maybe detect like a key point of like the top of the back of the chair and maybe like right where the person would be sitting in the center, and then like the 2 arm rests. But then we could take our model and apply it on chairs from outside in the atrium, and it would still work very effectively. So it's a really interesting area of research, and it's still very active in terms of how you can do these category level representations, and how you can have your networks extend to unseen instances or like even unseen categories maybe. So that's another one coming up. Let's see. So recurrent networks and object tracking. So everything up to this point that we've been talking about all assumes that our scenes are relatively static, right? It's like we're going to get an image, or we're going to capture a point cloud, and then we're going to try and produce some estimate, either like a pose estimate or a classification of the point cloud, but we're not assuming any motion, right? But the real world, of course, where our robots are operating is constantly changing. Humans are entering the scene, other robots are entering the scene, our robot is moving objects within the scene, and so how we can represent this change of the state over time is an important thing to consider for our perception systems. So the core papers that are identified here on this slide are all trying to somehow account for time or change in the scene using a neural representation. So like taking one example like this, like DeepIM, for example, would try to perform pose estimation, but pose estimation over time. So they would maybe have some initial pose estimate from their neural network at like time step 1, and then the question at time step 2 is, how do I refine my previous pose estimate given some updated observation? So I'm not sort of having to like start from scratch again, right? Because I had my initial estimate from the previous time step, but I want to maybe iterate that. So that's kind of one technique. I mean, another one that I think is really interesting is like pose RBPF. So pose RBPF, the RBPF part stands for a Rao black-equalized particle filter. So this is another example of a technique that was trying to kind of incorporate deep learning elements. So they used an autoencoder network, which I think we'll talk about in a few lectures. But essentially, it was a network that would sort of take in an image and then try to remove all of the noise from the image. So maybe you would take an image of like a very cluttered scene of objects where you're trying to estimate the pose of one of the objects in the scene. So maybe you can imagine like my desk up here is very cluttered. So maybe I would take an image of this scene, and if I was trying to estimate the pose of, let's say, like this screen, it would be really nice to have a network maybe that could like take this image from my perspective where it's very cluttered and somehow remove all of the pixels except the pixels that correspond to this object that I'm interested in. And then maybe perform pose estimation on that cleaned up, like less cluttered image. So Pose RBPF used one of these autoencoders in addition to some particle filtering techniques, which were one of those more classical pose estimation techniques, together. And what was nice about using those classical techniques is that the particle filter naturally accounts for time. So you filter over time. And so that's an interesting application of how you can maybe perform object tracking with these mixed neural network and classical techniques. An area then that's very close to my heart, because this is where I've done most of my recent work, is in visual odometry and localization. So if you're familiar with particle filters or Kalman filters or SLAM algorithms, these would all fit within localization. And there's been, I would say, like a flurry of work. Like there's been quite a bit of work just in the past maybe like 6 years that have looked at how you can embed neural networks into these classical filtering and localization algorithms. So for example, backprop KF, the one that's at the top of the slide here, the KF stands for Kalman filter. So this was a paper that proposed doing exactly that, taking the classical update equations that you would have in a Kalman filter if you were trying to maybe localize your robot in space, given some visual observation, let's say, and embedding neural networks to represent maybe like the covariance equations that you would previously have had to implement it by hand. So the nice part about embedding these neural networks in these classical algorithms is sort of twofold. On the one hand, the neural networks can represent some really complex patterns in the data that would be hard to encode by a human engineer. That's one nice thing. The second nice thing is that, let me think, what's the second nice thing? Well, so you get, and the second nice thing is you still get a lot of the interpretability of these classical algorithms, despite the fact that you're using neural networks. So one big concern that's being raised about neural networks is how we can trust them, right? So if you have like infrastructure critical tasks that you're performing, or if you're applying neural networks, let's say in like the judicial system, which is outside of robotics, but we should still think about it. There's a question of like, if the neural network is spitting out some answer based on the data it's seen, how can I really know what it was basing the decision on? It's like this big black box. And so I think one nice aspect of these works that are within visual odometry and localization is you still have some interpretability about your overall model, because the classical filtering algorithms that are being used with the neural networks are themselves probabilistic, and you can interpret, at least from the standpoint of probability theory. So backprop KF was one. Differentiable particle filters then followed that, where the particle filtering algorithm has some advantages over the Kalman filter because it can represent nonlinear state dynamics. So if you have robots that where maybe like the covariance in your state update should not just be a Gaussian, particle filters can account for that. And so this paper was a nice way of embedding neural networks within your particle filtering algorithm for localization. And then since then, there's been more work. So multimodal sensor fusion with differentiable filters was very cool, where now they're moving into like the manipulation scenario and trying to incorporate visual data with your differentiable filter as the robot is actually taking actions on the scene. And then differentiable SlamNet came out just, I think, like 2 years ago or a year ago, which is really impressive because SLAM is a very complex algorithm. And so they actually outperformed even like OrbSLAM and some of the like traditional human engineered feature extractors on the data sets that they looked at. This area is, I think, a very cool area. And there's an extended list too that's pretty big, if I remember from this area. So I know we're going kind of quick. So my plan will be to kind of like skim through just a couple more of these, and then we can break apart and start to maybe talk in groups about which areas are the most interesting, and hopefully you can sort of start to find partners that you might like to work with, or at least identify some of the papers that you might like to work with. So semantic scene graphs. So now we've kind of built up. So we had like this set of topics that we're looking at, sort of static scenes, and just asking like, if I have some perceptual data from a static scene, what can I do with a neural network, right? I could take in an image and maybe try and classify the objects in the image, or maybe taking an RGBD image and then estimate the pose of objects, or even for an entire category of objects, estimate the pose. And then with tracking, now you're starting to incorporate time. But we also have this question of like, the robot is not going to fixate on just single objects in the world. It's operating in an entire scene where there's lots of objects, right? So as I look out at this scene, or as you look at me, like think about how many individual objects there are, right? There's the carpet, all these chairs, the tables, the televisions, me, all of you. There's a lot of objects, a lot of things that are happening. And so how our robots can represent not just a single object in the pose of a single object, but this entire collection of objects, we should also be thinking about. And it's something that the deep learning community has been thinking about. So, Professor Justin Johnson, who sort of developed this course for the computer vision scenario, has done a lot of work for using scene graphs. So some of the early work was on how you could use scene graphs for image retrieval, where the neural networks would play kind of a component within that image retrieval task of maybe like classifying the difference between some of the images in feature space might be an indicator of how similar two scenes are. Our lab, Professor Jenkins' lab, has done a lot of work on trying to use semantic information for robot programming. So if you have some map, let's say, of an environment where you have semantic labels corresponding to different objects within the environment, then you can do a lot of interesting tasks with a robot given that knowledge, right? So you can start to understand like maybe how the semantic map should change if you have some goal condition you're trying to achieve. You can start to plan on a semantic map. So the robots can do a lot of interesting things, which these two papers identify. And then in addition, there's been work that looks at how you, and I should point out, like there's deep learning elements in those semantic robot programming projects. But to an even like kind of more extreme degree with deep learning, you can actually differentiate through scene graphs. So there's been work that looks at how you can maybe do like classification tasks in the context of scenes using differentiable scene graphs. Okay, so we're almost through with just like this broad overview. So now like one area that I think I've mentioned this past is like very, very, very active. I would say all of these areas are active, but Nerfs has truly exploded. And so what are Nerfs? Nerfs, so it stands for neural radiance fields. And so this, what you might say is like the original Nerf paper is this one up here. So you'll see this figure quite a bit. And what it proposed doing was if you took in a static scene a collection of images from different viewpoints, how could you train a new neural network that could be given as input the pixel locations and the pose of a camera and predict what the corresponding pixel color should be for this maybe unseen pose. And so what that is these are really, really effective. We can look at some of the websites and kind of like, because the examples are so cool to look at. But the reason why roboticists have taken, I think, a keen interest in these techniques is that if you can encode that information such that you could render this scene from novel viewpoints, you've encoded implicitly in this implicit representation kind of all the spatial information that you could hope to kind of capture, right? So you have the depth information because it's learning how the light is kind of being reflected off the objects and how the light is mixing. So maybe there's some depth information there. Obviously the color texture on these surfaces of the objects, maybe the implicit surface of the objects in terms of it being able to understand how the light is reflecting off of them, the texture properties of like how the light is reflecting and not just from where the light is reflecting. So all of these properties to some extent are getting baked into this neural network. So it seems like that neural network, once it's been learned, is like very, very powerful. Like we could maybe do a lot with it. And so roboticists have been trying to do a lot with them. So some of those earlier techniques that we looked at, right? So those like that idea of having like a very low level descriptor of an object in feature space. People have looked at how you could maybe use Nerfs to train some of those learned descriptors. Trying to combine object-centric Nerfs to compose a scene is an interesting idea because you can maybe use that for training or maybe use it within your planning routines to predict what the consequence of actions will be. Nerf supervision is a recent paper presented at this past year's ICRA that was similar to neural descriptor fields, so trying to like use a Nerf to on like doing point-to-point correspondences between the objects at from different viewpoints. And then you could use that for manipulation tasks, which they highlighted. So our lab has done a bit of work with Nerfs. So Stanley Lewis, another PhD student, this paper from IROS was looking at how you could learn a Nerf for articulated objects. So objects that are interrelated are more complex for a Nerf because they have that dynamic, that kind of dynamic articulation And so this paper looked at how you could still model them using neural radiance fields. Okay, then the last broad overview, and then we can break apart and start talking amongst ourselves, is the data sets. So there's an entire section of the webpage under the paper section on collecting like a pretty good number, but not, in the grand scheme of things, not that many of the data sets that exist. And it's important for us to think about where our data sets come from because we really rely on them for all of our deep learning. So robots play a pretty big role within data set collection, but also for our robots, if we're gonna have perception models for them, we need data sets. So large-scale data collection with robots is one area that is very, very interesting if you can afford many, many robots. So this work from Google, this first paper that's on the far left, proposed collecting data about like how robots are manipulating objects in parallel. So if you take like 100, I don't remember which robot arms they're using, but if you take like 100 robot arms and you have them running 24/7 trying to manipulate objects and then collecting data on how they're manipulating them or what they're seeing when they try to manipulate objects, you can collect a large-scale data set. The downside, though, is you have to be able to afford all that robot time and also all the engineers that go behind keeping those robots running. So a much more affordable approach is to simulate your data sets. So NVIDIA, for example, the GPU chip manufacturer, has invested an extraordinary amount of money into rendering with high fidelity. So in addition to that, if you have like a good action model of the world, you can render very high fidelity and very accurate robot simulated data sets. And so that's a big area that you'll see a lot in like reinforcement learning, especially. But then alternatively, if we can't maybe afford like these really large scale data set collections with physical robots, but we might not want to use simulated data because it can bias our model by what's referred to as like the sim to real gap. So if you train a model on simulated data and then try and apply it in the real world, usually your performance will drop because it's sort of overfit to that simulated environment. So if we find ourselves in that position, then we have to get creative about how we collect data. We have to do it very efficiently. So some of these other papers that are cited on this core section are really clever ways, I think, of trying to collect a large-scale data set for deep learning, but doing it efficiently. So like the grounding predicates through action paper, for example, was like looking at how you could maybe, if you have knowledge about some like video sequence of data about which actions are being taken, you can actually derive how the state is changing because you know what the preconditions and postconditions of those, let's say, already labeled actions are. The All You Need Is Love paper is really fascinating. They use like ultraviolet tags on objects to actually collect. So I kind of forgot some of the specifics, but what they would do was they would take an image in optical color, and maybe that would be what they were ultimately hoping to train an RGB network on. But then at the same time, then they would turn like off the color lights and turn on a black light, and then take a UV photo where there's now like UV paint labeling maybe like the pose of the object or something to that, or maybe like the segmentation of the object. So as a result of this, they could automatically annotate all of the UV collected data because maybe like if the segmentation of the object is just apparent, you just get it automatically. But then at the same time, they have the color data to train their network on, so they don't have to do like much human annotation. So I think some of those questions about like how we could efficiently collect data is also important for us to think about because academia is certainly interested in that question. And so in this rundown that I've done, we didn't even cover all of the areas. So there's even more areas that are listed on the website for your final project areas. So like grasp pose detection, tactile perception is where you're trying to use maybe like sensory data in terms of like the force contact when the robot starts to touch objects in the world and how you could use that for perception. Transformer architectures are increasingly becoming prevalent. And then there's even more. So I think what would be good now is to sort of break away into like maybe for those of you who are sitting at each of your tables, or if you're not sitting at a table with other people, feel free to just join the nearest table and start looking over the paper list and seeing which papers maybe stand out. We've covered just in this presentation, I think probably on the order of like 40 papers, just at a very high level, but some of them hopefully are interesting to you. So I'll turn off my mic and I'll kind of walk around and see what people are thinking.